July 12, 2022 marked the beginning of the James Webb era, as NASA released the first proper pictures taken by the iconic infrared observatory. Webb's first set of images is not only magnificent in appearance, but also contains a treasure trove of scientific information. So, what new did the James Webb Telescope discover in these images? How are they significantly better than those captured by the Hubble Space Telescope? Finally, and most importantly, how will these images give astronomers a deeper understanding of the universe? Let us begin with the first image that NASA chose to release, a galaxy cluster named SMACS 0723. It is the deepest and sharpest infrared image of the distant universe ever taken by a telescope. Every pixel of this picture is overflowing with details. Let's start with the brightest spots with spikes in this image. They are the stars of our own galaxies, more like the objects sitting on our noses. Around the center of the image lies the galaxy cluster about 4.6 billion light-years away. So the light we are seeing now was emitted from these galaxies 4.6 billion years ago when the Earth was forming. But this is just the beginning of the details that this image contains. Due to its combined mass, a galaxy cluster bends the light from the background objects. This effect is known as gravitational lensing, and was predicted by Albert Einstein using his general theory of relativity in 1936. The galaxy cluster comprising the bright, elliptical galaxy in the center and smaller white galaxies distorts the light path from the background galaxies. And because of that, we see lensed images of even farther galaxies that are otherwise out of our view. Webb's deep field image portrays gravitational lensing in a way we've never seen before. One can see prominent orange arcs on the left and right sides of the brightest cluster galaxy. These represent the lensed galaxies, with individual galaxies popping out twice in the arc. However, not all galaxies are mirrored. Some also appear stretched as a result of the magnification. And surprisingly, the galaxies located behind the cluster look nothing like the spiral or elliptical galaxies we find in our local universe. Instead, they look comparatively clumpier and more irregular. This very thin arc is one of the most magnificent objects in this image that truly demonstrates the power of the James Webb Space Telescope. Hubble barely detected this arc, but Webb sees the beads on a string clearly. They're likely individual star clusters in the extremely distant, tiny galaxy. We can see similarly amazing details all over the deep field. For point-like objects, Webb is expected to be beyond 100 times more sensitive than Hubble. In the background, faint red galaxies appear scattered all over. And when Webb took the spectra of one such galaxy, it found signatures of oxygen, hydrogen, and neon flourishing there. This makes Webb the first telescope to reveal such details of a galaxy that is more than 13 billion years old, bringing us closer to our origins. And the most astonishing fact is that the Webb's entire deep field image covers a patch of sky about the size of a sand grain held at an arm's length by someone on the ground. After the condensed deep field image, NASA revealed a transmission spectrum of a scorching exoplanet lying almost 1,100 light-years away. It's a hot Jupiter named WASP 96b, with a mass of less than half of Jupiter and a diameter of 1.2 times more. WASP 96b lies so close to its parent star that it takes just 3.5 days to complete one orbit. As a result, the temperature in this world exceeds 1,000 degrees Fahrenheit or 540 degrees Celsius. The spectrum taken by Webb reveals the planet at infrared wavelengths, to which we had no access before. Webb studied this hot Jupiter planet using the traditional transit method. This method analyzes the starlight's dimming when the planet passes across its disk as seen from Earth. The light from the parent star gets modified as it passes through the orbiting planet's atmosphere. Astronomers then compare this filtered starlight with the unfiltered one to study the exoplanet's atmosphere. On June 21st, Webb's near-infrared imager and slitless spectrograph was used to observe this planet as it transited its star for 6.5 hours. In the spectrum, 141 data points appear as white circles, and each one represents the amount of a specific wavelength of starlight blocked by the planet and absorbed by its atmosphere. The gray lines surrounding each data point are the error bars showing the uncertainty of each measurement. Considering that the data resulted from a single observation, the error on these measurements is remarkably small. Further, the blue line is a best fit model that is considered to deduce the system's properties. A complete analysis of the spectrum will take time, but as per preliminary analysis, the labeled peaks in the spectrum indicate the presence of water vapor, although less than expected. The next Webb image is of a planetary nebula, a dying star about 2,500 light-years away, known as the Southern Ring Nebula. NASA released 2 images of this nebula, one captured by the near-infrared camera, or NIRCam, and the other by the mid-infrared camera, or MIRI. A planetary nebula forms when a sun-like star ejects its outer layers at the end of its life. This near-infrared image captured by NIRCam shows a very bubbly view of a nebula, with its structured shells also visible. The orange hue represents the newly formed molecular hydrogen during expansion. At the same time, the blue haze signifies the hot ionized gas heated by the core of the host star. The best thing about Webb's image of the Southern Ring Nebula is that it revealed something that astronomers predicted long ago. The bright star you see in the Hubble image of this nebula is in an early stage of evolution, so astronomers knew that a dying star must be nearby that was responsible for the Southern Ring Nebula. Unfortunately, however, no telescope could ever find it, but Webb's advanced infrared capabilities did the job. MIRI finally found the source of the nebula, a dying star surrounded by gas and dust. As the star turned into a white dwarf, it periodically ejected mass. The process repeated. The star contracted and heated up, eventually ejecting at least 8 layers of gas and dust over thousands of years. And the accompanying star helped it in stirring the material. Webb has captured this image with unmatchable details. There's also a bright angled line that appears to be a gas filament from the nebula itself. But astronomers found it to be a distant edge-on galaxy when they investigated the light source. Further, many distant spirals of different shapes and colors, some very small, dusty, and red, enhanced the overall view. The fourth image in Webb's collection is an enormous mosaic of Stefan's Quintet, a visual cluster of 5 galaxies captured by NIRCam and MIRI. Although this group is referred to as a quintet, only 4 galaxies can be seen close together, with the 5th lying in the foreground compared with the other 4. And what makes this image extremely special is that it is the largest image taken by Webb. It contains over 150 million pixels and is constructed from almost 1,000 separate image files. This image flaunts clusters of millions of young stars. Also, sweeping tails of gas, dust, and stars being pulled from some of the galaxies due to gravitational interactions are visible. MIRI has also captured huge shockwaves as one of those galaxies. NGC 7318b is smashing through the cluster. The regions surrounding the central pair of galaxies are shown in the colors red and gold. One can see a distinct difference in color between the dust in the galaxies versus the shockwaves between the interacting galaxies. The image specialists have used yellow and orange colors to indicate the difference in MIRI data, in contrast to the blue and white colors assigned to stars at near-infrared wavelengths. A deeper analysis of this image can offer fundamental insights into how galactic interactions may have driven galaxy evolution in the early universe. The Carina Nebula is perhaps the most beautiful image of the first set. Unlike the Southern Ring Nebula, this one is a star-forming region about 7,600 light-years away. This spectacular image revealing previously invisible areas of stellar nurseries was taken with the joint forces of Webb's NIRCam and MIRI. With its crisp resolution and unparalleled sensitivity, NIRCam has unveiled hundreds of previously hidden stars and even numerous background galaxies in this image. We can see bubbles and cavities blown by the intense radiation and stellar winds of newborn stars. Also, some protostellar jets of golden hue are being blown out by the infant stars. There are hot stars on the top rim of the image, and their radiation pushes down the dust and gas to further condense it into more stars and baby planets. However, at the same time, intense radiation can also erode gas and dust, halting star and planet formation. So in one way, this image represents a balance in the ongoing polar phenomenon and shows how our solar system once formed in such an environment. The steam that appears to rise from the mountain-like structures is hot, ionized gas. Each such structure is about 7 light-years or 42 trillion miles tall. The formation period of a star lasts only about 50,000 to 100,000 years. This makes early star formation extremely difficult to be captured. But with Webb's sensitivity and unprecedented spatial resolution, we have been able to record this rare event and hope for more spectacular observations every coming week. Webb's first set of scientific images hinted at what the telescope can do. A new era of astronomy has begun, and we can't wait to see what Webb reveals next. If you enjoyed this video, make sure to like it, subscribe to our channel, and press the bell icon so that you don't miss any video of this series.